The voltage readings you are observing suggest that the motors are connected in a delta configuration. Let's break down why you're seeing these particular voltage values. In a delta configuration, the three phases are interconnected in a closed loop. Each phase is directly connected to the other two phases, forming a triangular arrangement. This connection method has significant implications for voltage and current behavior within the system. The defining characteristic of a delta connection is that the line voltage, which is the voltage measured between any two of the three phases, is equal to the phase voltage, which is the voltage across each individual winding. This is different from a Y configuration, where the line voltage is the phase voltage multiplied by the square root of 3, approximately 1.732. In your case, the readings show that the voltage between phases A and B is 486 volts, between phases B and C it is 492 volts, and between phases C and A it is 486 volts. These values are relatively close, indicating a balanced three-phase system. The slight variations could be due to minor imbalances in the load or measurement inaccuracies. The fact that the phase-to-phase voltages are approximately equal to 486 volts confirms that the motors are indeed connected in a delta configuration. Now let's examine the voltage readings between each phase and ground. You reported that the voltage between phase A and ground is 486 volts, the voltage between phase B and ground is 486 volts, and the voltage between phase C and ground is 0 volts. This is an unusual and potentially problematic situation. In a properly grounded delta system, the voltage between each phase and ground should not be equal to the phase-to-phase voltage. There are two main possibilities to consider. Firstly, the system may be a corner-grounded delta system. In a corner-grounded delta system, one of the three phases, in your case phase C, is directly connected to ground. This means that the voltage between phase C and ground will be 0 volts, as you observed. The voltage between the other two phases, phases A and B, and ground will be equal to the phase-to-phase voltage, which is approximately 486 volts in your case. While corner-grounded delta systems are permissible, they are less common than other grounding methods due to certain safety and operational concerns. Secondly, there could be a fault in the system. A ground fault occurs when one of the phases comes into contact with ground, either directly or through a low impedance path. In a delta system, a single ground fault will not typically trip a circuit breaker or fuse, as there is no complete circuit for current to flow through. However, it does raise the voltage of the other two phases relative to ground to the full phase-to-phase voltage. If a second ground fault occurs on a different phase, a high fault current will flow, and the protective devices should trip to clear the fault. Based on your voltage readings, it is likely that you have a corner-grounded delta system or a ground fault on phase C. It is crucial to investigate further to determine the exact cause. Here are some steps you can take to troubleshoot the issue. Firstly, verify the grounding configuration. Check if one of the phases is intentionally connected to ground. This can usually be determined by visually inspecting the grounding connections at the service entrance or at the transformer supplying the power to the motors. Look for a solid connection between one of the phase conductors and the grounding electrode conductor. Secondly, perform a thorough inspection of the wiring and equipment. Look for any signs of insulation damage, loose connections, or other potential sources of ground faults. Pay close attention to the motor windings, the wiring inside the motor junction boxes, and the conduits and raceways that carry the conductors. Thirdly, use an insulation resistance tester, also known as a megometer, to measure the insulation resistance between each phase conductor and ground. A low insulation resistance reading indicates a potential ground fault. The specific insulation resistance value considered acceptable will depend on the voltage rating of the equipment and the manufacturer's recommendations. However, as a general guideline, an insulation resistance of less than 1 megohm is often considered indicative of a problem. Fourthly, use a clamp-on ammeter to measure the current flowing in the grounding electrode conductor. In a properly grounded system, the current in the grounding electrode conductor should be very low, typically less than a few amps. A high current reading indicates that there is a ground fault somewhere in the system and that current is flowing through the grounding path. Fifthly, if you suspect a ground fault, you can use a ground fault locator to pinpoint the location of the fault. Ground fault locators work by injecting a signal into the grounding system and then tracing the signal to the point where it is leaking to ground. Once you have identified the cause of the problem, you can take the necessary steps to correct it. If it is a corner grounded delta system, you may want to consider changing the grounding configuration to a different type, such as a high resistance grounded system, to improve safety and reliability. If it is a ground fault, you will need to repair the damaged insulation or replace the faulty equipment. It is important to note that working with electrical systems can be dangerous, and you should always take appropriate safety precautions. Wear appropriate personal protective equipment, such as insulated gloves and safety glasses, and energize the circuit before working on it. If you are not comfortable working with electrical systems, you should consult a qualified electrician. Here is some additional information that may be helpful. The delta configuration is commonly used in three-phase power systems for several reasons. Firstly, it provides a higher starting torque for motors compared to a Y configuration. Secondly, it is more tolerant of unbalanced loads. Thirdly, it does not require a neutral conductor, which can save on installation costs. However, the delta configuration also has some disadvantages. Firstly, it is more susceptible to voltage imbalances. Secondly, it does not provide a convenient neutral point for single-phase loads. Thirdly, it can be more difficult to protect against ground faults. There are several different types of grounding systems that can be used with a delta configuration. These include solid grounding, corner grounding, high resistance grounding, and ungrounded systems. Each type of grounding system has its own advantages and disadvantages, and the best choice will depend on the specific application. Solid grounding provides the lowest impedance path to ground, which helps to minimize voltage rise during ground faults. However, it also results in high fault currents, which can damage equipment. Corner grounding, as discussed earlier, involves grounding one of the phase conductors. This is a simple and inexpensive grounding method, but it can create safety hazards if a second ground fault occurs. High resistance grounding uses a resistor to limit the current flow during ground faults. This helps to reduce equipment damage and improve safety. Ungrounded systems do not have a direct connection to ground. This can improve the reliability of the system, as a single ground fault will not cause a trip. However, it can also make it more difficult to locate ground faults. When working with delta-connected motors, it is important to understand the voltage and current relationships in the system. The line voltage is equal to the phase voltage, and the line current is equal to the phase current multiplied by the square root of 3. The power factor of the motor will also affect the voltage and current readings. A low power factor can cause the voltage to drop and the current to increase. To improve the power factor, you can install power factor correction capacitors. These capacitors will supply reactive power to the motor, which will reduce the amount of reactive power that the motor draws from the power system. This will result in a higher power factor and improved voltage regulation. It is also important to properly size the conductors and protective devices for delta-connected motors. The conductors must be sized to carry the full load current of the motor, and the protective devices must be sized to protect the conductors and the motor from overloads and short circuits. The National Electrical Code, or NEC, provides detailed requirements for conductor sizing and overcurrent protection. Refer to NEC Table 310.15 for conductor ampacity ratings and NEC Section 430 for motor circuit protection requirements. Remember to consult a qualified electrician for any electrical work.